All right, so here's the problem that we're going to look at. We have a roller coaster at the top of its path. It's going to come down into the first dip and go up the up to the next hill. Now the problem is that this particular roller coaster has been designed as though the first hill and the second hill are the exact same size. We're going to talk more in depth about why that's a problem a little bit later on, but you can probably just from personal experience understand that that is not going to work. So the situation here that we have a roller coaster. We see its weight up here is 2,202 pounds, and it is initially on the path at a speed of 2 meters per second, and that's it. It starts from a height of 35 meters, and it doesn't quite make it up the hill. The hill is bigger. Well, it's going to be 35 meters. They made it the same size, and it only makes it 28 meters up the hill. So the first thing that we're going to do, this is a two-part problem. Part one is we are going to try to find the energy lost to friction. Okay? And part two, okay, I'm going to give you some more information for part two, so know that you only need it for part two. If the track length is 88.8 meters long, what is the average force friction? So at this point in time, I'd like you to try to pause and do as much of this problem as you can. That might mean that you just do your given and find, maybe a force diagram and get stuck for 5 minutes, but see what you can do. I'll tell you right now, we are going to be using the work net kinetic energy theorem. Makes sense. That's what we're working on right now. And yeah, you're going to see me do that here in just a second. So pause. I'll see you back here. You're back. Okay. So let's go over this particular problem. The first thing to identify is what the heck does it mean by energy lost to friction? Well, in a more simplistic put, that is energy changed because of friction. So that's the name it told us, but ultimately we have to recognize that that is how energy is changing. Thus, what that is asking is that is the work of friction. Okay? And secondly, what is this? Well, it already knows that's force friction. If the distance is 88.8 meters, I'm just going to go ahead and erase this for right now, and we will use it at the very end. So what is the work done by friction? Not entirely sure how to solve this problem, so I'm going to begin with how we always begin, and that is a force diagram. So let's come over here, and let's do a force diagram. Now, what you might have noticed is that this force diagram is a little weird. Because it's going down like in changing angle the entire time, that technically means the force diagram is going to change. So I'm going to pick a spot kind of here in the middle-ish, and I'm just going to do the force diagram right here and consider what effect that will have as it goes through. Okay? So force gravity, doesn't matter which way it's pointing, it's going to go straight down. If I look at this spot, force normal would go here, and force friction is going to go back. And there are no other forces. While this roller coaster is on the track, there's nothing pushing it other than gravity itself the entire time. So I've got three possible forces. What's my next step? My next step, here's my given, sorry, my fine. My next step is to do the work net kinetic energy theorem. Okay? And then we expand that out. This is where we're always going to start. So we have to learn to start here and expand outwards. How do we expand out the work net? Well, this is the combination of all of the works. So I'm just going to look at each force and write a work for each of them. Okay? And then kinetic energy always expands the exact same way. Final minus initial. And it's at this point in time that I usually look to try to cancel what cancels. So let's start, because they cancel differently, let's start with the left side. Okay? Even though the force diagram is changing, one thing that we have to consider is that a lot of things change together. For example, force normal. Which way does force normal go? Perpendicular to the surface. So if the displacement, if the way the object is going is always parallel to the surface, well, then force normal is going to change, but they're going to change together. So even though they are changing, you'll notice that the angle is continuously 90 degrees, which means that work of normal is still going to be 0. Okay? Work of gravity. Well, unlike force normal, force of gravity does not change direction. It stays straight down, so we need the distance straight down. Is it going to go straight down at some point in time? Is it going to head downward? Yes, so that's not going to cancel. Finally, friction also deals similarly to what we were talking about with normal. Okay? While it is going to change direction, it's always going to point the opposite way of velocity. So if this is my displacement as I go down, I start going this way and then roll down the hill and then come back up, friction is going to be the opposite direction of that. So even though they are changing together, and thus this is going to stay at 180 degrees. That being said, I got to remember, what am I looking for? What I'm looking for is the work of friction. A big mistake that somebody would probably make in this problem is going immediately to this right here. We know to get work, you take force times displacement times cosine theta. Now, I did just tell you what that particular angle is, and if you skip ahead to B, you technically know what that displacement is. We'll talk more in a second. We don't know how much force friction is. As a matter of fact, we're trying to find that in part B, so we cannot use this. But if you come back here, what you'll notice is I could just go ahead and find this piece right here. We're still on canceling stuff out to 0, so neither of these, like we said, will cancel. This will probably be positive. That'll probably be negative. But right over here, we have kinetic energy final. In other words, right there. Is it moving right there? No, it stops. So that would be 0. Okay? Kinetic energy initial. Is it moving at the very beginning? Yes. So that does not cancel. Now, I like to do the algebra at this point in time. I could start introducing in individual equations, but I definitely don't want to introduce an individual equation in for this one since I'm trying to find the total thing. So I'm just going to go ahead and subtract work of gravity on the other side. Work of friction equals negative Ki minus work of gravity. How do I get Ki? Well, that's minus 1/2 mass Vi squared. How do I get work? Well, that is force of gravity. And right here, actually, let's just go ahead and use Wg. That is force of gravity. Sorry, Wg, mg. We could either use the F displacement cosine theta equation, or we can use this one. And this one makes way, way, way more sense, because to use this equation, I would need to figure out what this displacement is and figure out what the angle between this displacement and gravity is, and that's really messy, especially when the purpose of this equation is to figure out how much displacement is parallel. Since gravity is going straight down, all I need to figure out is how much this goes straight down. Since it starts at 35 and ends at 28, I know that the displacement downward, or the change in height, is 7 meters. So I'm going to multiply by the change in height. Now, technically, there is still a cosine theta. I got to think, all right, which way is that change in height? Downward. Which way is the gravity? Downward. So those are same direction. Angle is 0 degrees, so that would technically be multiplied by 1. And then we can go. We don't know mass, so we are going to have to do stuff from last chapter real quick here. I should probably do that conversion. So that's 1 pound is equal to 4.45 newtons. My calculator. 2202 times 4.45 gives me, let's just go ahead and round this to 9,800 newtons. Mass times gravity equals force of gravity, so mass equals force of gravity divided by g, so that's going to be 1,000 kilograms. Let's plug in what we know. Minus 1/2 times 1,000 kilograms times velocity initial is 2 meters per second, because that's how fast it was going, minus 1,000 kilograms times g times the change in height should be 7. Notice that that is a positive 7 right over there. Again, the negative comes from the cosine. And we know, again, it's going 7 meters down and gravity is down. They're the same way. So that's cosine of 0 degrees, or 1. The final answer of this, and multiply that all out, should be negative 66,600 joules. Now, one shortcut we're going to be using, because joules are going to get kind of big in this type of problem, is what you can always kind of feel free to do, so you're writing less zeros, you're writing a little bit smaller numbers, is just do this. The prefix kilo means times 10 to the third. So what I could do is I could move this decimal place over, 1, 2, 3, and get that that's negative 66.6 times 10 to the third joules, or negative 66.6 kilojoules, which is a little bit nicer way to put this. You do not have to do this particular part. That's just me working out exactly how to do it. But this is the answer to part A. How do I get the answer to part B? Well, that's where this equation comes back in. Work of friction is equal to force of friction times displacement times cosine theta. We now know that this value right here is negative 66.6 kilojoules, or negative 66,600 joules. So we want to know, what is the average force friction? The reason we say average is because that equation does assume that friction stays constant, which it wouldn't here. Some of these spots have more force normal, and therefore will have more force friction. But we're usually just going to assume that that's constant so we can get the average. And from here, we would just get this by dividing those two underneath. Work of friction, displacement times cosine theta of friction equals force friction. This would be negative 66,600 joules. Yes, you do have to use joules here. The question is, what displacement goes there? Well, like I pointed out earlier, the displacement of the object and friction are kind of going, the object's going this way, right? It's going along with the track. It's going parallel to the track. So gravity stays straight down, so the distance that we need goes that direction, goes straight down. Friction stays parallel to the track, so what we need is this distance, the track length, because that is parallel to the track. That is the track. That is that 88.8 meters that I gave you on part B. So we should divide by 88.8 excuse me, meters. The angle, as I mentioned earlier with friction, displacement's going down, friction's going the opposite way. So even though they are changing directions, the angle stays at a solid 180, which makes that just cosine of 180, and that's going to go to -1, and that negative will cancel with that negative. And if I divide all this out, I get that the average force the entire time is 750 newtons. If you need to do this problem again, I would not blame you. Okay, it's certainly not an easy one, but this is kind of the level that we're trying to get you to. That's it.